When we discuss polynomial functions, one thing we're going to be able to do and want to be able to do is to find zeros. And one thing we're going to use in particular is called the Intermediate Value Theorem, which allows us, if we know two particular points on a given function, then we can figure out what might be happening between those 2 points. And before I get into stating what the Intermediate Value Theorem is, think of it this way. If I give you this problem, can you go from the point 3, 4, so can we go from this point here, to 5, -2 without crossing the x-axis? And the rules are you can't lift your pencil. In other words, you can't just say, oh, okay, we'll go here, and then now I'm magically on this side. You can't do that. And rule number 2 is you can't leave the grid. In other words, you can't just go around it like that. Our goal, again, we want to go from our first point here, we'll call this A, 3, 4, we'll call that A, and we want to get to B. We want to get from A to B, and let's see if we can get there without crossing this x-axis. I could give you a few minutes to try it. If you want to hit pause, you can do that, but I'm going to give you a hint. You'll be sitting there for a while, because it's not going to happen. There's no way that we can get from A to B without crossing the x-axis. Again, the two stipulations, we could if we could just pick up our pencil and then magically go to the other side, but we're not allowed to do that. And theoretically, I mean, here we see that the x-axis stops, but really this would be going on in this direction forever, so we wouldn't be able to do that. So again, the reason or the answer to this, can you go from point A to point B without crossing the x-axis? The answer is no, you cannot. These two rules, especially rule number 1 here, that you can't lift your pencil, that is an important fact. And let's now get into what this means and how this ties into the Intermediate Value Theorem. The Intermediate Value Theorem says for any polynomial function p of x with real coefficients, if we have some a and b, in other words, two inputs, if we plug those a and b, if we plug them into the functions and we see that they're opposite signs, then there must be a 0 between a and b. On our last slide, we saw that we had one point, let's call it a, one point that was above the x-axis, and we had another point, let's say b, that was below the x-axis. So here we say we have some a and b, and when we plug them in, right, keep in mind what's making point A here above the x-axis, what that means is that when you plug in a, p of a was greater than 0. It was a positive number because our output, we plug in a and we go up, so our output was greater than 0. Down here for p of b, if we plug in b, what we see is that when we plug in b, our function happens to be below the x-axis. That means our function is less than 0. Since this is a polynomial function, and we know polynomial functions are continuous, and that ties back into the rule that we're not allowed to lift our pencil. So if we wanted to go from this point A that has a positive function value, and we traveled along this curve, and we wanted to get to this point B, which has a negative function value, since it's a polynomial function, we can't lift our finger, we can't lift our pencil. That means there must be somewhere between A and B where this particular function crosses the x-axis. That's what the Intermediate Value Theorem says. Since when we plug in A, we got a positive value, it was above the x-axis, and when we plug in B, we get a negative value below the x-axis, then somewhere between A and B, we have to cross the x-axis. In other words, somewhere between A and B, our function, p of x, somewhere between there has to equal 0. So if you were asked to determine whether or not a 0 exists between two particular values for a function, what you would have to do is first plug in A, So you're given two x values. You plug in the first, so we'll call that A. Plug in A. Then you'll plug in B. Plug in your other value. And then compare their signs. If they are opposite signs, then we know there must be a real zero between them. If one of them is positive and one of them is negative, then because of the intermediate value theorem, we know there has to be a zero somewhere between them. If both of them are positive, there still may be a zero between them. We just can't state that. We'd have to try something else. And same thing if they're both negative. That doesn't mean there isn't a zero between them, but we just need to do more work. What we're going to be using the intermediate value theorem for is seeing if one's positive, one function value is positive, and the other one's negative, then there must be a zero between them. Let's look at an example. We are given a function f of x equal to x to the third plus x squared minus 8x. And we want to be able to determine if there is a real zero between the x values 1 and 3. We don't necessarily need to graph these. When we can figure out algebraically, and we can use the intermediate value theorem to test whether or not there is a zero between them. Just because we use the intermediate value theorem, and if it doesn't work, that doesn't mean that there isn't a zero between them. You would have to make sure to go about checking some other way to see if there was a zero between them. But the intermediate value theorem, at the very least, if it works, then we know for sure. If it doesn't, we might have to check something else. So what this is saying is we have an x value of x equal to 1. We'll call this our A, and we're going to call our x equal to 3, we'll call that our B. And that's similar to what's happening on that graph that we had. When we had that graph, we had a value of A and we had a value of B. And we wanted to see if they connected. So what we want to be able to see is where is A? When we plug in x equal to 3, what is the sign? Is it above the x-axis or is it below? And then we're going to do the same thing with B. When we plug in 3, is it going to be above the x-axis or below? If we find out that one of them is above and one of them is below, then there has to be a point between them where it crosses the x-axis. So let's do that. Let's find f of 1. We'll plug in our first value and we'll see what we get. So when we plug in 1, we get 1 to the third plus 1 squared minus 8 times 1. So our function evaluated at 1 gives us 1 plus 1 minus 8, which we see when we plug in 1, we get a negative 6. So really what's happening, we're plugging in 1, and if we were to mark that point, we would have the point 1, negative 6, which would be maybe right here. Maybe that would be our first point. This is let's label this our A. Okay, so now that we have our real A there in blue, let's figure out where our other point is. Let's plug in x equal to 3. So our function, when we plug in 3, will be equal to 3 to the third power plus 3 squared minus 8 times 3. We're plugging in 3 for x. And we get, 3 to the third power is 27, plus 3 squared is 9, minus 24. So if you were to simplify that, 27 plus 9 minus 24 is going to give us a value of 12. So that point is 3, 12. We plugged in 3 into our function, we got 12. That would maybe be all the way up here, and we'll call this our B. This is a good sign. Okay, since we see that when we plugged in f of 1, we got a negative value, and when we plugged in x equal to, or f of 3, we get a positive value. We get a positive 12. Since when we plug them in, one of them's positive and one of them's negative, we know that whatever's happening between those two values, it has to cross at a 0. So determine if there is a 0 between x equal to 1 and x equal to 3. Since 1, we plugged in 1 and we got a negative value, and we plugged in 3 and we got a positive value, we see the answer is yes. There must be a real 0 between them, and we know that because of the intermediate value theorem, which states that for a polynomial function, there has to be a 0 between those 2 points.